Hey guys, so in this video we're going to finish up the back side of notes set 15. We made it a little bit through, but we still have the bottom half of the page here that we need to finish up. So pull that out. Let's zoom in. Crunchy noises. So this whole set of notes, notes 15, is on gases. This is just a reminder. It says up here at the top, note set 15, gases. We were trying to explain relationships within the gas state. We were looking at like, how are pressure and volume related? How are the pressure and the temperature related? If the temperature goes up, what happens to the pressures? You get more pressurized in the container, whatever. And we called this KMT. This was the kinetic molecular theory. And this was why gases behave the way that they do. The kinetic molecular theory, there were several assumptions that we made. We assumed, I should have it on a separate page here. We assumed that the particles exert no forces on each other, aka there's no intermolecular forces. We assumed that the kinetic energy of the particles was directly proportional to the temperature. Things like that. These were all the assumptions that were being made, whether they were true or not. Most of them are okay to assume. It's okay to assume that the particles themselves are so small that it doesn't matter what the identity of the gas is. But one of them that is super duper fake is assuming that there's no IMFs. There are still IMFs, and it does throw off our calculations a little bit. We're going to talk about more of that. But the first thing we're going to address is that the average kinetic energy of the particles is directly proportional to the temperature. So looking here, this is called a Maxwell Boltzmann distribution chart. And it kind of looks like those early graphs at the beginning of like the COVID era, when they were like, we need to slow the spread, like hospitals can only, like see this many patients, so we can't exceed that line because then these patients up here won't be getting care. So we might still have the same number of cases, but we need to spread them out. That was the idea when COVID was first happening. So what a Maxwell-Boltzmann distribution plot is, they look like this. It's a graphical representation of the energies or the velocities of the particles at a given temperature. AKA, we're looking at the kinetic energy, AKA movement of the particles versus the temperature in kelvins. The Kelvin temperature of a sample is proportional to the average kinetic energy. So the higher the kinetic energy, the higher the temperature. They run the same. This graph is a little bit hard to read stagnant on a piece of paper, but what this is trying to show you is we're looking at the area underneath the curve for let me switch my marker because I don't like this pink one. I want to use a different color. Hi, Daisy. I know you really want me to pet you, but I'm recording a video. You want to say hi for the video? Come here. Come here. Come here. Come say hi. Okay. Okay. Here we are. Oh, no, let me switch to camera. Say hi. Hi, cutie. Yeah, you don't like the attic. We're in the attic and the heat rises. And so she gets really hot up here with all this fur coat. You good now? I petted you. I said hi. Can we go back to the video? All right, so with these, we're looking at the area, and I'm going to use blue marker because this first curve is referring to a cold gas. So I want to use blue because that seems colder in my head. And this would be the distribution of particles. We'd have graphing all of the points, like these are all of the speeds of the cold gases. And as the temperature gets warmer and warmer, it's almost like we're pinching this and drawing it out into a more elongated shape like this. We still have the same number of particles. If I wanted, I could count out and make sure that this curve has the same amount as this curve. All we're doing is spreading it out, just like with the COVID cases. If we knew, let's pretend that 100% of people were going to get COVID, so 100, this would be 100 people getting COVID in a short period of time. This would be 100 people getting COVID in a longer, more spread out period of time. Instead, now we're looking at the speed of the particles versus the number of particles. We still have 100 here versus here, but the average speed of the cold gas, I would say the average speed is, there's no numbers, so slow. While the average speed of the hot gas is a lot higher. Which makes sense because the higher the temperature, the faster the movement. So let me do a screen share and show you a Desmos. Here's a Desmos kind of simulation. It's showing right now, it's just got one curve. If I were to change the temperature, let's say I'm going to change the temperature and make it warmer, the average speed would go up. Right now, the average speed of this hump looks like, I don't know, dragging this down. I'd say the average speed is like 225, it looks like. If I were to draw a straight line here. If I kick the temperature up, the average speed is going to go up, the center of the hump. So let me crank up the temperature. In order to do that, though, I cranked up the temperature, but notice that the number of particles is changing, and it's still the same area under the curve. I've just changed, are they all together, or is it more spread out? So this is showing the effect of temperature. The colder the temperature, the more it's all over to the one side. And then the higher the temperature, the average speed, notice, let me crank it all the way up, 1,000 degrees. At 1,000 degrees, instead of whatever this number is, at 1,000 degrees, my average speed looks like 500 instead of an average speed of 200 over here. So that's the effect of temperature. If I reset all of these, and instead of looking at how temperature affects it, the other variable that's on my little Desmos thing is showing the atomic weight. So if I'm looking at the atomic weight, the bigger the atom is, the slower it's going to move, whereas tiny particles move really fast. We already talked about this. Tiny particles like go fast. So big ones are like moving slow. So if we had a particle, let's see. I'm adjusting this low. Notice 40, 38, 36, 35, 32. I'm making it go less, 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 less. And the speed is increasing for something like, let's see. Let's see, carbon weighs 12. It's a pretty light particle. So the red here is showing the carbon. The average speed of carbon under these conditions would be 500. Whereas something that has an atomic mass of 60, I don't know what that is. Let me pick something I actually know. I know that chlorine is 35. So here in green, chlorine is running at a speed of 300 on average. There's some fast ones, there's some slow ones, but on average, chlorine's traveling at about 300. Whereas carbon is about 500. So questions you might expect to see like on the AP test or something. This is an actual, why are my bangs being so weird? Here's a question that's going to be on your test, like for high class. It's a conceptual one. Let's do a share screen of it. The diagram above shows the distribution of speeds for a sample of N2 gas at 25 degrees Celsius. Which of the following graph shows the distribution of speeds for a sample of oxygen, O2, at 25? So, let's see. Izzy, are you okay? You're coughing. You got the coughs. All right, 1 second. Ugh. Sometimes her little trachea collapses and then she goes like, y'all better now? Thank you. Okay, I gotta get this back on screen, share dog. Okay, so looking here, we've got nitrogen. I don't like that pen color. Got N2 at 25 degrees. And we're wondering down here, which of the following in like the dashed line would be O2? So thinking about nitrogen versus oxygen, check your periodic table. How much do each of those weigh? Nitrogen weighs, nitrogen is 7, isn't it? Number 7, so it weighs 14 for each nitrogen. And oxygen is 15.999. So oxygen is about 16 per. So O2 is going to weigh 32. N2 is going to weigh 728. This is really difficult on Microsoft Paint. So looking at the speeds, we can expect the 32 to be going slower than the 28. So on all of these, this first line is nitrogen. This one, O2, on average, it is going slower, and it looks like the graphs that we had. This next one, I don't really know what this shape is. It looks weird, so we're just gonna, nope, not choose this one. This one is showing that it would be, the average speed would be faster, but we don't want it to be faster. We're trying to show that the oxygen is slower because it weighs more. So not that one. And over here, again, it's showing that it's faster, but I'm not even convinced that those are the same area. So not this one. So here's a conceptual one. This one is based off of the weight. You might be asked to do some other ones based off of the temperature, or in this case, the weight. So back to the notes then. It's just showing the average, go from the center, follow it down, and then if it has numbers, you'll be able to see the numbers on average. So this corresponds to the average kinetic energy of the particles is directly proportional to the temperature. The other thing that I'm addressing in this video is this part B, where it says, assume that particles exert no forces on each other, aka that there are no IMFs. This is absolutely not true. All states of matter have IMFs, even gases, but sometimes we ignore them to make our calculations more simple. Ideal gas law, the one that we did the other day, this one, ideal gas law, PV equals nRT, perv nert. The ideal gas law does not explain the actual behavior of real gases. It's a good, oops, that's blurry. It's a good estimate, but it's not real. It's like Mulan, where she's trying to be like the perfect daughter or whatever, and she can be because she's a real person and real humans make mistakes. So that's what you got to think of when we're doing ideal gas law calculations. So we're assuming falsely that there are no intermolecular forces. The intermolecular forces are what clump particles together and keep them like this instead of spreading out. We're assuming that there are none, but that's false. And so whenever you have a deviation from your ideal gas law calculation, it's probably because there are IMFs that are causing the gas to clump up more than our fake prediction is assuming. So the conditions, this graph, excuse me, I have some in my throat. This graph is a little bit hard to read. It's just showing, it's a, what is this called? What is this called? Good Lord, I'll think of it. It's just showing the states of matter here. We've got solid, liquid, phase diagram, that's what this is. Solid, liquid, and then vapor is what it says, but gas. You're going to be the most gas form. If you're trying to be a perfect and ideal gas, then you stay as far away from solids and as far away from liquid conditions as possible. So if solids are here existing in kind of high pressure, low temperature situations, high pressure, low temp, then you're going to want to avoid that to be an ideal perfect gas. Liquid is kind of high pressure, medium between, but we're specifically trying to be as much of a gas as possible, as much in this perfection gas corner as we can be. This is where the most ideal of gases would be. The closer they get to that liquid condition or the solid condition, the less ideal they are behaving. It's like when your parents want you to be the most ideal child and they're like, stay away from those types of people because the closer you are to them, the less ideal you are. So the conditions that the gas is going to be ideal is going to be, let's see if this is pressure on this axis. We're going to want low pressure and really high temperature. These are the conditions that ideal gases exist under. So on your test, either in my class or on the AP test, if it's asking like, what conditions are most suitable for the ideal gas law to apply, you'll say, to be the most ideal gas, we need to be the most in this corner, away from solids and liquids. We need low pressures, high temperatures. And here's a sample example of a question that you might expect. consider the following samples of a gas. We have helium. The helium, I'm going to do in orange. Helium gas at 600 torr and 40 degrees Celsius. The other one is, dropped my green marker. Okay. The other one is SO2 gas at 600 torr and 40 degrees Celsius. Same conditions, really the only thing that's different is the identity of each of the gases. So we need to, part A, find the density of each gas, okay? Then we need to find the average velocity, the root mean square velocity of the gas in each container. And then there's going to be a discrepancy that we're going to need to explain. So for right now, we're going to assume that these are ideal gases because we have nothing else to go off of. The ideal gas law is PV equals nRT. We do have to do some conversions here because the pressure needs to be in atmospheres instead of torr. The volume, well, I'm just going to write down all of these. The volume would need to be in liters. N would be number of moles. R is a constant. We just have to use the right one. And T is the temperature in kelvins. If density equals the mass over volume, and the molar mass of something, like, looking at the periodic table, and the molar mass of CO2 would be carbon plus oxygen plus oxygen. The molar mass, notice I've got that weird symbol there. The molar mass is the mass over the moles. I'm going to rearrange these two equations, actually these three equations here, so that I can have, let's see. You don't need to worry about this. I'm just doing a rearrangement for you. Rearranging. The formula for the density of the gas is going to be the molar mass times the pressure over RT. This is just some math that I did off to the side, combining all of those formulas. You can just memorize this if you want. It'll work every time. So if we're finding for part A, we're going to find the density of the helium gas, He. Then I need the molar mass. The molar mass of helium is 4. Let me look at my periodic table here. Technically, it's 4.026 grams per mole, according to my periodic table. M times the pressure. The pressure is 600 torr. There's 700 torr in an atmosphere. So I've got 0.85 atmospheres. R is the gas constant, which is 0.0821 with all the units. T for temperature, the temperature is 40 degrees Celsius. To convert into kelvins, I add 273. My temperature is 313 kelvins. All right, this is the density of helium. the density of helium, it's like how compact it is equal to I do it right. Let me just put in some extra parentheses to make sure. Okay, so I'm getting the density of this is 0.134. Density is mass over volume, so grams per liter. This is the density of helium. To get the density of the, what is it, the SO2? Obviously, this one is going to be a lot more dense. Like helium is a very lightweight particle. It only weighs 4. SO2 weighs, there's 2 oxygens, and I think the sulfur weighs 32. I think it's like 64-ish is how much this guy weighs. So the calculation will be the same, the density of SO2 instead of helium equals, same, everything's going to be same as above, but I got to change the weight because all of the conditions were the same. 600 torr, 40 degrees Celsius. But now instead of only weighing 4 on the periodic table because it's helium, we're going to weigh 64 because of SO2. The density being I'm getting, actually, I did this wrong for both of them because when I did my conversion here, I think I did just 600 over 700. I should have done 760 and been more exact because there's 760 torr in an atmosphere. So let me really quick go back and fix this. We're actually not at 85. We're not at 0.85 atmospheres. We are at 0.789 atmospheres on both of these. So let me real quick, let's recalculate. Here's my original one with the 4.789. Okay, now I'm getting 0.124. Let me switch that over here. Just a tiny difference. I just don't want it to be confusing later. Okay, that's our density of helium. And now same calculation, but switching from 4 to 64.07. The density of this one is 1.967 grams per liter for SO2. Okay, if I lost you there, let me do a little quick summary. We have 2 gases. One of them is helium. Helium is a tiny, tiny particle that weighs 4. SO2 is a big one that weighs 64. So when we look at the density, which is the mass over volume, obviously this is a more dense gas because it weighs more in the same amount of space. A liter of SO2 is going to weigh about 2 grams. A liter of helium will weigh only 1/10 of a gram. We have a weight discrepancy between these two. Helium weighs 4 grams per mole. SO2 weighs 64 grams per mole. That is going to affect the density, which we can see. It's also going to affect the the velocity that these gases are going in the container, kind of similar to up here, how sometimes they move slower, sometimes they move faster. This one's based on temperature, but that Desmos one that I was showing you, we can play with the weight, and you can see that the faster one will be the lighter weight one. Let me get this all adjusted. Actually, we can punch in the exact weights. Let's do it. The atomic weight of the first one is 4. Here's our helium curve. Zoom out so we can see the whole thing. Let me swap this so you can see my face. Hello. So this red one is the helium. The SO4 we said weighs 64. Nope, too far. 60. I can only do 63 or 65, really. Okay, I guess we'll go with 65. Dang it. Okay, I tried my best. So 4 and 65, because I can't quite get it where I need it to be. But look at the speeds. The average speed of the helium is like way out here. And the average speed, according to this simulator, would be way low down here. I don't know if these numbers are accurate, but you can try it. And try it and see. Because according to my little Desmos simulator, this speed of the SO2, since he's a big boy, would be like 250. But the helium would go like almost 1,000. But I don't know. We'll play with it and see. All right, so to figure out the speeds of these, we're going to want to go back and look at the, let's see, the formula up here. The VRMS, the velocity, the root mean squared, is the square root of 3RT divided by the molar mass. The molar mass needs to be in kilograms. So part B, I'm finding the average velocity. The VRMS, I'm going to do helium in orange. The VRMS of helium is the square root of 3RT over the molar mass in kilograms. Square root of 3 times. Make sure that you pick the right R value, which in this case is the 8.31. Remember up here, 8.31 joules per mole Kelvin. The temperature in Kelvin was, we already converted this, 313. The molar mass is 4 grams per mole, but in kilograms, I gotta divide by 1,000. 4.026 divided by 1,000. That's good enough. The speed of the helium is square root of 3 times 8.31 times 313. We'll simplify that. Times 313, I like that better. Divided by 0.004026 equals 1,392 meters per second. That's how fast supposedly the helium is going. And if I go back to my little let's see, let me pull up my Desmos chart. Was that anywhere near the right number? Share this graph. Okay, so this graph says that my temperature's off though. I got to get it to 313 Kelvin. How am I supposed to know what this is? Doesn't even tell me. Ugh. I don't know. I don't know what the, I guess, if I'm guessing, I'd say that that's 300 because here's 0 and here's 1,000. Anyway, I can like, oh no, I don't want to touch that. I touched something. Okay, that looks like 300. So let me just match these kelvins up. Actually, it's not so bad, right? My helium is here in red. My calculation says that 1392 is the average speed. Check it out. It looks like it might actually be right. So under the same conditions for the big chunkest molecule, the SO2 that weighs 64, let's see if we can get a number. It's about 300. Doing the same calculation, but instead of the 4 down bottom, I'm going to plug in the 64 instead of the 4. 0.04 would be 64. And what do you know? That the RMS for SO2 is 349 meters per. So actually, the Desmos simulation isn't half bad because that's pretty much what I was saying, like 300-ish right there. Big gas goes slow, tiny gas go fast. B is more what you would expect to see on the AP exam. Part C as well. Part C says that each container has a half mole of the gases in it. Each container has 0.5 moles of the gas. The volume of container A was 16 liters, while the volume of container B was 15. Explain the discrepancy between the two. So technically, according to our assumptions, we assumed that the identity of the gas was irrelevant. But it turns out these two gases with different identities take up different amounts of space. The helium takes up 16 liters. The SO2 takes up 15. What's up with that? That's the question. I know, do you have a backside of this paper? I don't. I'm going to draw on it. The helium, which is tiny and only weighs 4 grams per mole. Actually, that's irrelevant. I don't even need that. Helium versus SO2. It says that the SO2 takes up 15.96 liters of space. The helium takes up 16.07 liters of space. Why? Shouldn't they take up the same amount of space? Ugh, so frustrating. Well, the reason that the helium takes up more space is that helium is more ideal of a gas than SO2. This one is less ideal, which means it's more real. Real gases have intermolecular forces. Intermolecular forces are the stickies that try and keep things together. So if this one has real IMFs that are making it clump up, it makes sense that it would have a smaller volume. Helium has no intermolecular forces. It's a noble gas. So there's nothing squishing it together. It spreads out more, no interactions, nothing sticky stringing it together. So it takes up a little bit more space. The more intermolecular forces you have, the smaller your volume will be. You'll be less ideal, and you will have bigger deviations from the ideal gas law. So anytime that you deal with a gas that has IMFs, because it's polar, this one's polar, I don't know if you remember, but that's a polar molecule. This one's not. Polar molecules specifically have IMFs. They're pretty big IMFs. So you'll get a lot more squishy closeness happening. And that's the discrepancy that it's asking about. So to answer this question, I would say, explain the discrepancy between the two. Although kinetic molecular theory states that the particles are so small compared with the distances between them, we assume the particles take up zero space and have no IMFs. This is not true. The IMFs present in SO2, due to it being polar, cause clumping to occur. There you go. And that is notes set 15.